So we've already reviewed Grubler's equation for a slider crank and a 4-bar and a couple other mechanisms. And we noted that one of the reasons we like slider cranks and 4-bars so much is there's only one degree of freedom. Mobility is one. Or, in other words, we need one actuator, let's say one motor or one piston. Well, what if you want your 4-bar to have a certain motion? If you're listening to this at the beginning of the semester, we've just learned Grashof's Criterion, which breaks our 4-bar into general categories, which I'll review: double crank, crank rocker, double rocker, change point, and triple rocker. You've either will or you already have, as a lab, created each of these categories of 4-bars in SolidWorks, so visually you can get a sense for how they move. But if we're designing a crank rocker, for instance, where one side can go all the way around, the other side rocks back and forth, this is just overall how to get the mechanism. Later in the semester, we'll learn a couple techniques for getting exact motion. That if I wanted to rock from one position to another or to pass through three positions, for a slider crank, we'll look at a vector loop method called Freudenstein's equations. For 4-bar, we're going to use graphical methods for that to define either how the coupler moves through 2 or 3 positions or how a side rocks. Right now, these are general categories. And in class, I've been using small script letters here. I've used a combination of small and cap. So, to remind you, this is Grashof's criterion for a 4-bar mechanism. S is the length of the shortest link, L is the length of the longest link, and then you have the two intermediate length links, and not shortest or longest. Those we're calling P and Q. And so the Grashof's criterion says if I add up the lengths of the shortest and the longest, and it's less than the total length of the other two, at least one link can revolve a full 360 degrees. Maybe more than one can, but at least one can. This doesn't mean that it won't hit the frame, hit the ground, or something else, but if I suspend my mechanism properly, it can revolve all the way. Non-Grashof would tell us that none of the links can revolve all the way. They're just going to rock. One is fixed, and the other three will rock back and forth. So you have in your notes already these categories, the criteria, whether it's less than P plus Q, equal to P plus Q, or greater than P plus Q. And then we need to know the shortest link is which side. So if we take a look at the top for my double crank, let's turn this a little more into a 4-bar. So we have the ground. These joints are pinned. And if we think back to using Grubler's equation for mobility, we always call the ground link, which is our frame. Right? So this is our frame where the two grounds are connected. We have the sides. I can go either way. So I'm just going to go this way, 1, 2, 3. Our sides are 1 and 3. So this is a side. This is a side in this notation. And this one here is referred to as the coupler. Okay. And I shouldn't call that 1, sorry, that's 2. So we have 1, 2, 3. And then I'll call this one 4. Okay. The order there, it doesn't matter. Pin joints A, B, C, and D. So what do we know from before? So N is 4. Primary links is 4, the 3 pins A, B, C, D. We don't have any sliding joints, otherwise known as prismatic. And we don't have any higher order, such as gears, such as a cam and a follower. And if we plug it into the equation from Grubler's equation, we know already we'll get 1. If you don't remember that, I have the other reviews already posted as video. So 1 degree of freedom. So now the question is, and this is true for all of these, what is a double crank? So if the shortest link is the frame, so that's this link right here again, and the lengths are measured at the connection points. So connecting A to D. Right, if I have a general physical link that's larger, I'm always measuring from the pin connection. those are the lengths that I'm actually using. So if the frame is the shortest, it's a double crank. So what's a double crank mean? It means both these sides, this one on the left and this one on the right, can spin a full 360 degrees. So you put a motor on it, for instance. Remember, you have to design it so it doesn't just slam into the frame or the ground or something else. A crank rocker, and again, I haven't measured these, but you've already done this or will be doing this in SOLIDWORKS. So we got a pin there. So the crank rocker says the shortest link is the side. So again, with our nomenclature, it's 1, 2, 3, 4, and I can put the same thing. We can letter these. I'm going to get the same mobility calculation. So this side, I believe always the shortest side, is going to go completely around. So this one's going to go the full 360 degrees. I can put the motor here. This one on the left is only going to rock back and forth. So it'll just move to some other position. And as I mentioned earlier in the review, we'll learn how to size these exactly if I wanted to rock, let's say 20 degrees, 40 degrees, and figure out what lengths I need. But for right now, this is just a general classification. A double rocker, this third case down, has the shortest at the coupler. So it's the shortest at the coupler. Again, I have not measured these, so it's possible any of these could fail under that last non-Grashof criterion, S plus L S plus L greater than P plus Q. But assuming it doesn't, this is the case we have. So what is a double rocker? So double rocker basically says this one here can only go between a certain distance and a certain distance, not all the way around. Let's take a look at a triple rocker and talk about the difference. Let me just jump to the bottom for a moment. I'm getting back to that dead part of my screen. And move it up, that should work. Yep. So what's the difference? Well, simile is only going to rock back and forth, in other words, not go 360 degrees. So what's the difference between a double rocker and this triple rocker? Triple, screen issues there, it jumps, and double. So on a triple rocker, even this coupler can only rock back and forth. Where in a double rocker, this one right here can go the full 360 degrees. So again, you can find videos online where people have done this, but you'll be doing this in your lab, creating this and seeing this yourself. So the double rocker, the coupler can spin completely around, and the triple rocker, all the links, all three links can only rock. Change point. What's interesting about a change point is used all the time, but it's a parallelogram. So if I connect the ground here, right, this is the same as this, and these are the same. And we see this all the time in mechanisms. The problem with a change point is, well, the advantage of a change point is as it's coming down, let's say this set, let's see if I call this link 1, 2, 3, and 4. As it rotates, link 3 stays parallel to the ground. So it's a good mechanism for that. The problem is once it becomes a straight line, basically when these links overlap, we don't know what's going to happen on the other side. In other words, right, they come down, and they start overlapping. And when they come through, let me put it over here. Nope, might be a little bit easier, sorry. When they come through, I have a couple things that can happen, right? They could basically, oh, we're on the crazy part of the screen already. They could end up looking like that. Or, let me jump down here. This part seems to be working. One part could come down. The other part could end up coming up. Sometimes they call this an anti-parallelogram. They call it a butterfly arrangement. And what you'll see with SolidWorks, hopefully, is that sometimes it just goes crazy on you. And it's not that you put it in wrong, it's getting confused. So it works fine as long as I don't crank it to the point that it goes flat. But if I try to crank it all the way around, it doesn't necessarily know to come completely around. So it doesn't know whether to do this condition A here or this condition B. And hopefully the SolidWorks lab will support those visuals.